Let's try to solve this problem here. So a car of mass 1500 kg accelerates from rest and attains a speed of 20 meters per second in 12 seconds. So we are going to visualize this situation here using a diagram. So let's say we have something here to represent the ground, and you have a car here, and this car, as mentioned in the question, is 1500 kg. Then it's going to accelerate from rest. So initially it's going to have an initial speed of 0 meter per second. Then after that it will undergo motion, okay, a certain journey, and throughout this journey it is undergoing a constant acceleration. And at the end of this journey over here, you see that this car here will have a final speed of 20 meter per second, and this journey here takes around 12 seconds. Okay, not around, take exactly 12 seconds. So this is a situation, and we are going to study what? Let's look at the question. The question asks for the kinetic energy of the car when the speed is 20 meters per second. So we know the information regarding the mass of the car, the speed of the car. So to know about the kinetic energy of the car will be quite direct. It's just using the formula of kinetic energy. So kinetic energy is equivalent to half mv squared. Okay, so now it's just substitution. Half the mass of the car is 1500 kg, and the final speed of the car is 20 meters per second. So if you substitute everything in and you calculate, I believe you get an answer of 3.0 times 10 to the power of 5 joule. So this is the amount of kinetic energy possessed by this car over here after finish the 12 seconds journey. Then that's the kinetic energy, or the energy associated with the motion of an object. Okay, let's move on to the second question. After achieving a speed of 20 meters per second, means that after this point over here, the engine of the car is switched off. Then the car travels a distance of 200 meters before stopping. So you can imagine a situation like this. Initially, the car is at rest. Let's say you just start your car, then you step on your accelerator pedal, then the car speeds up because you step on the gas pedal, then the car speeds up at a constant acceleration. So you don't suddenly press a lot, you suddenly press a little, you press at a constant angle. So yeah, the car speeds up until you reach this point. Once it reached the final speed of 20 meters per second, what you do after that is you immediately switch off the car engine. Then you shift it back to neutral gear. Let's say shift the car back to N. Then what the car will do is the car will continue to move in the same direction, but as it moves it will slow down because there's air resistance and there's friction, various factor will bring the car slows down to a stop. So the question statement here says that this car will travel for another 200 meters before stopping. So let's draw it. So you imagine the car will continue to move after the engine is being switched off. Then it will travel for a distance of 200 meters. So this is 200 meters before stopping. So I believe this will be 0 meters per second. We cannot put 2v over here. We have 2v over here. So let's label one as v2, let's label another one as v1. And let's label this point here as the point where you switch off engine. Okay. Now, they ask what is the retarding force on the car? Retarding force means by the force that is retarding the motion, or opposing the motion, or obstructing the motion. Retarding means making it harder or making it less and less. Okay, so retarding force over here means by the car is moving in this direction, what is the force acting in the opposing direction to slow down the car to a stop? Okay, so we are going to relate between speed, we are going to relate between distance, and we are going to relate between force. You know that distance and force here are parameters that you need to calculate work done. So you know you need to involve work done. And speed here can be related to kinetic energy. So you have to relate between the work done and kinetic energy. And what kind of theorem will relate between the work done and the kinetic energy? Well, it's the work energy theorem. So you know for this question, you have to use the work energy theorem. So to solve a question, you have to see what are the information being given and how they relate from one physical quantity to another. In this case, the speed here can be related to kinetic energy, and the distance and the force here are directly related to the work done by a force. So you need to relate between the total work done and the work done by the force later. Okay, so let's go through it step by step. You know that you need to use the work energy theorem. So work total is equal to change of kinetic energy. You know that the delta here is just final minus initial. So this is final kinetic energy minus initial kinetic energy. But for this part over here, this is slightly complicated. Total work done. It's the work done by all the forces acting on an object. So what are the forces acting on an object? We have to determine it using a free body diagram. So let's use this dot here to represent the car. And we have an axis parallel to the road and an axis perpendicular to the road. So this car has mass, therefore it has weight. And this car is touching the floor, therefore you should expect there's normal force. And now because this car is in the motion towards the right without any engine, okay, that you switch off the engine already, right? So since you switch off the engine, you should expect there is no force in the direction of motion, because if you step on the pedal, then the engine is giving a thrust to the car, forcing the car in this direction. But now since you switch off the engine, there is no force pushing the car in the direction of motion. What's left is only the force that is opposing the motion, such as the air resistance or such as the friction. Various kind of forces are trying to slow the car down to a stop. So you should have a retarding force. Let's summarize all the forces that are opposing the motion right now as retarding force. So you say we have a retarding force, let's label it as FR, retarding force. Okay. So if you analyze everything, you'll see that these are the only three forces that are acting on this car over here. So our work total here will be a combination of work done by the normal force plus the work done by the gravity or work done by the weight and the work done by the retarding force. So these are the three forces that can do work on the object. But I believe we are clear with the situation here. The situation here, our object is having a displacement in this direction. So again, when we talk about work done, you have to look at the angle between the force and the displacement. For the normal force and the displacement, the normal force and the displacement are 90 degrees with each other. So we know that the work done by normal will be equal to 0 because it's cos 90 degrees. And the work done by gravity or the work done by weight here will be 0 as well because the weight and the displacement is also 90 degrees. So since these two forces are having a 90 degree with the displacement, you should expect no work done by these two forces over here. So what can you see? The work done by the normal force will be equal to 0. The work done by gravity will be equal to 0 because they are 90 degrees. Okay, so your total work done now is equal to the work done by retarding force right now. The only force that is doing work on the car is the retarding force. So now you have modify your equation to be work done by retarding force equals to the final kinetic energy minus initial kinetic energy. Okay, so this is how we do it step by step. The work energy theorem is always total work done equals to change of kinetic energy. You cannot change this to a work by a single force. Okay, you have to find all the forces that are acting on an object, prove that all the other work are equal to 0, then the only work left will be your work total. So what am I trying to say here is, if you write work work by retarding force is equals delta K in your first line, technically is incorrect because you haven't proved that the total work done is only the work done by the retarding force. So if you write that straight away, right, it's wrong. You should write work total equals to delta K, then slowly work through the process step by step. Okay, so I remove this. Okay, so now once you have reached this step, you can expand the line now. The work done by the retarding force is just the magnitude of the retarding force, Fr, the magnitude of the displacement, and cosine the angle between the retarding force and the displacement. The retarding force is pointing here, the displacement is pointing here. One left, one right, so the angle between them should be 180 degree. So this should be 180 degree equals to half mvf square. Let's don't use vf. I think in here we use v1 and v2, right? So this should be half mv2 square minus half mv1 square. Okay, so now let's move on to substitution. The magnitude of retarding force, we don't know, we leave it as Fr. The displacement is 200 meter, then cosine 180 degree equals to half. The mass of the car is 1500 kg. The V2, the final speed is 0 because it comes to a rest at the end. So minus half 1500. The initial speed when you switch off the engine is 20 meter per second. So now the only unknown that you have here is the retarding force. So you can use your calculator to calculate everything. And you find the magnitude of retarding force to be 1500 Newton. Okay, so the retarding force here has a magnitude of 1500 Newton. What you obtain here is the magnitude, because based on our formula here, this is the magnitude of the force, magnitude of displacement, cosine the angle between the force and displacement. So this is just the magnitude, but if you wish to write everything clearly, the magnitude and the direction together, what you can do is you can see the retarding force vector is equals to, you write the magnitude first, then after that you write the direction. You don't exactly know whether the car is moving to the left or moving to the right, so what you know for sure is it's opposite the direction of motion. So you can write the direction by saying that it's opposite the direction of motion. Okay, so this will be how you can use the work energy theorem to relate it with relate the total work done with the change in kinetic energy, thus relate it to the change of speed.